Okay, everyone, can you guys see me and hear me okay? Awesome, thank you. All right, one more thing. Okay. Happy Wednesday, everybody. We have just one more week of classes left, which means I will see you guys just twice more after today before your final exam. So first thing that I want to do is say thank you to the 54 of you who have joined class today. That's about a third of the class. So I think everybody is, kind of triaging their time, but I appreciate your time since you guys are respecting my time. So what I'm going to ask everyone to do right now is in the chat box, please write your name and your favorite color. And I will go back in, and everyone who is here today will get some participation points for writing your name and your favorite color, really just for showing up, because that's half the battle. Okay, so today we're going to talk about chapter 10, which is the synthesis of alcohols. Obviously, everybody probably is thinking about exam 3, which you guys just finished up. I will probably release the part 1 scores today or tomorrow. The grading, my hope is that it will be done on Friday, if not over the weekend. But we're, everybody's busy at this time of year, so we're just doing the best we can and trying to get it done as soon as we can. But today our focus is going to be on chapter 10, the synthesis of alcohols. And just to remind everybody, I do have my typical office hours today. I will be in my office, so in real life, but I will also have my Zoom link open. And so we'll do like we have been doing, where we're kind of just going around the room and taking turns where every person can ask one question, and then we go all the way back around. The other reminder I have for you guys today, I mentioned this last week, but we will be having a quiz on this chapter 10 material. However, it will not be during any kind of class time. It will be an open book quiz, and it will be a take-home quiz. And so I'll talk more about that on Friday, but just know there's one more kind of grade chunket coming before the final exam. And then there will also be an achieve homework coming for chapter 10. So those are going to be the last 2 grades of the main portion of the semester before the final exam. And we'll talk more about all of that on Friday. But for today, like I said, I want to focus on the synthesis of alcohols. So before we get started with the synthesis of alcohols, so someone's asked in the chat box, when is Achieve due? The Achieve, I think, is going to be due on Monday because of the last day of classes, but it's going to be a very short assignment. And we can discuss if you guys want a little bit of extra time. What I don't want to do is have you guys have too many assignments that are lingering after the formal end of classes. So right now I have it, I have plans to set it to be due on Monday, but if that poses a problem, then that's no problem. And your final exam is Friday of next week. It's on May 6th. So Friday of next week is when your final exam is. And we'll talk more about all of this stuff in, not today, but in probably briefly in the next class, and more detail on Monday of next week. Okay, so our outline for today is not actually our outline for today. It is actually our outline for the whole chapter. Today we are going to jump around a little bit and selectively cover structure and properties of alcohol. We're going to skip over nomenclature, and then we'll just kind of keep going on down this list, and we'll get into a fair amount of organometallics today. So you guys already know a lot about alcohols. We are going to draw from things you already know from chapters 1 and 2, and I'm going to put it together for you so that you can really get a sense of how we can apply those same concepts from chapters 1 and 2 and apply them here now in chapter 10 to understand a little bit more about the structure of alcohols and about what that means for how they will react, right? So let's go ahead and get started with that. As you guys know, when I'm talking about alcohols, I'm talking about compounds that contain hydroxyl groups, or this OH bond scenario. So we can, just like with other functional groups that we've seen, we can apply the term alcohol just to the functional group, and we can say this is an alcohol, or we can apply it to the overall molecule that contains an alcohol functional group. And of course, you can kind of go either way on that. Alcohols are something that you guys are probably very familiar with. They're very useful compounds. They're around in nature, they're around your house, they're used in industry as solvents. Of course, we all know ethanol is a very good disinfectant, and of course can also be ingested in moderation and carefully. Methyl alcohol is actually toxic. It will make you go blind. You may have heard of wood alcohol. This methyl alcohol, if it gets into your body, it gets processed into toxins that are very harmful. And isopropanol, the third of these are the three kind of simplest alcohols. Isopropanol is just rubbing alcohol. It's the same rubbing alcohol you can go to the drugstore and buy. It's the same rubbing alcohol that is in most of your hand sanitizers out there. Our structures of alcohols are going to be very familiar and very comfortable because it's going to be just like water, right? So our alcohols, just like our water, they're going to have an oxygen that is sp3 hybridized. Remember, it's sp3 hybridized because it has two lone pairs, and each of the lone pairs needs its own hybridized orbital to help it repel against all of the other lone pairs. So remember, our hybridization in general is based on VSEPR theory, so valence shell electron pair repulsion theory. So we've got a pair of electrons in each, represented by each of these lone pairs, and a pair of electrons in each of these sigma bonds. So all four of those pairs of electrons need to be able to repel each other, get as far away from each other as possible. And in order to do that, they need to achieve a tetrahedral geometry, which is going to be achieved by having an sp3 hybridization. Of course, that also means that the alcohol itself has a bent geometry because we don't really count the lone pairs when we talk about the molecular geometry, but the hybridization does make the oxygen sort of a tetrahedral oxygen with the molecule having an overall bent shape. The angles are just like you would expect for a tetrahedral. They're around 109.5. They're a little bit compressed in this case because the lone pairs take up so much space that they're compressing the sigma bond angle. You guys don't need to worry about that or remember those numbers. Just know that they're close to the tetrahedral angle of 109.5. Okay, so in terms of how we categorize our alcohols, this should also feel really comfortable and familiar to you guys because this is the same categorization method we've used for alkyl halides, we've used for carbocations, and we've used for carbon-based radicals now. Whatever carbon that oxygen is attached to will have a designation based on how many carbons it is attached to. So in this example up at the top, this carbon marked with a blue star is attached only to one other carbon. That makes this carbon a primary carbon. That means that anything associated with this carbon will get a primary designation. In this case, a primary alcohol. If this had been a carbocation, it would be a primary carbocation. If this had been a bromide, this would be a primary halide. This is a primary alcohol because our hydroxyl group is attached to a carbon that is attached to only one other carbon. Likewise, our secondary alcohol is a hydroxyl group attached to a carbon that has two carbon-carbon bonds. And following suit, there is our tertiary carbon. Now, our newest sort of member with a new terminology here is aromatic OH groups. So when that hydroxyl group is on a benzene ring, that benzene ring is also known as a phenyl ring or PHENYL. And so when we put a hydroxyl group on a phenyl YL ring, then it becomes a phenol with an OL designation in the suffix, and that OL is the same OL suffix that comes from the word alcohol. So a phenol is a benzene ring with an OH group on it, and they have specialized reactivity, as we'll see kind of moving forward. Okay, in terms of the properties that alcohols have, these properties come directly from the fundamental concepts that we were learning about in chapters 1 and 2. The key features are going to be based on the capability of alcohols to do hydrogen bonding. And so just a refresher from way back when, hydrogen bonding is fun, right? FON. That means that in order to have hydrogen bonding capabilities, we have to have a hydrogen that is covalently attached to something that's very electronegative. Fluorine, oxygen, nitrogen, those are fun, right? Hydrogen bonding is FON for fun. When you do that and you have your hydrogen covalently attached to a strongly electronegative element, the bond is highly polarized. The hydrogen atom has a delta H that is very electropositive, and that makes it capable of having an interaction with the lone pair on another molecule of your compound in question. When you have something like an ether, even though you have these lone pairs on the oxygens, you don't have a highly polarized bond here anymore, and so you cannot interact between the atom bonded to the oxygen and the lone pair on another oxygen. So only the alcohols can undergo hydrogen bonding and not ethers. And you can see that this aspect, this is one of the intermolecular forces, the strongest, in fact, intermolecular force that we learned about in chapter 2. And you can see that reflected in the boiling points of these molecules. So here's an example. If we look at ethanol versus dimethyl ether, these are the same molecular formula, which makes these two compounds constitutional isomers, right? They have the same molecular formula, but the order that the bonds are connected are different between those two. And in the case of ethanol, this highly polarized OH bond is capable of hydrogen bonding. But in the case of dimethyl ether, all of our hydrogens are attached to carbon. There's not a single hydrogen anywhere in this molecule that is attached to a strongly electronegative element. So dimethyl ether is not capable of doing hydrogen bonding. You can see that both have a pretty decent molecular dipole because of the geometry of the molecule and the directionality of the lone pairs on the oxygen. However, the one that can hydrogen bond has much stronger intermolecular forces. And so ethanol has a boiling point of 78 degrees Celsius as compared to dimethyl ether, which has a boiling point of negative 25 degrees Celsius. So this, you can see, yes, ethanol has a little bit more polarity to it, but this is a dramatic difference in the boiling point between these two compounds. And that difference is explained by the hydrogen bonding that is capable for ethanol and not something that dimethyl ether is capable of, even though they have the same molecular formula. Okay, so we talked briefly about solubility of alcohols, but alcohols are going to be, the solubility of alcohols is also going to be helped out or dictated in part by this hydrogen bonding. So the alcohol portion, the actual hydroxyl group, can interact favorably with water. And so if you have a small R group here, then it's this favorable interaction with water that dominates. And so smaller alcohols like methyl alcohol, ethyl alcohol, and propyl alcohol, those are completely miscible with water. You can mix them up in any combination and they're totally fully soluble. However, as you begin building a larger and larger R group on your alcohol, this larger R group is not compatible with water solubility. And so at some point it gets big enough that your alcohol becomes only partially soluble in water or sometimes not soluble at all. So these are going to be competing aspects of an alcohol, and whichever one wins out is going to have to do everything with kind of how big and how hydrophobic that R group is. So just the same way as how this R group increases and the solubility in water goes down as this R group increases, the solubility in organic solvents also goes up at that same time. And that should make sense because most organic solvent molecules are hydrophobic as well. Okay, so the other aspect that I want to talk about with respect to alcohols is also something you already know from chapter 4, I believe, possibly from chapter 2. Actually, it's from chapter 2, the acid-base chapter, and that is about the acidity of alcohols. So I've asked you guys already back in chapter 2 to remember the pKa of water and other similar alcohols as being around 16. And indeed, you can see all of these different alcohols have a pKa in this kind of comfortable range here. And of course, as you add on electronegative elements, your pKa drops because that electronegative element helps to stabilize the conjugate base after you deprotonate. But overall, these are all still pretty much in the comfortable same range as what we've been talking about. Another thing I want to point out, and I'll have a couple more slides about this later, is that the pKa of phenol, so a hydroxyl group attached to a benzene ring, is quite a bit lower, like dramatically lower. And we'll talk about why that is in a little bit. So first, let's talk about how we can generate what's called alkoxide ions, which are the deprotonated version of alcohols. So one way, of course, is to just get a stronger base and mix them together and affect a deprotonation. So if we had, for example, sodium amide, which we know is a stronger base because it's a strong enough base to deprotonate a carbon-carbon triple bond, a terminal alkyne, it is also a strong enough base to deprotonate an alcohol. So we could do it that way. The other way that we could do it is if we take our alcohol and incubate it with sodium metal, like sodium 0. Because of the placement of sodium in column 1 of the periodic table, sodium is ready and able and willing to give up an electron. That is a very favorable thing for sodium to do. Give up an electron to become sodium plus, because sodium plus has the same electron configuration as an inert gas. And so it's favorable for sodium to give up an electron. When it does that, if you're putting electrons into this system, what happens is that eventually you put in enough electrons to break this oxygen-hydrogen bond and generate your O minus. Of course, you are also going to have to generate something else. So what happens is if you put enough electrons in, you have enough electrons to build a new sigma bond between the two hydrogen atoms that were originally your hydroxyl group hydrogen atoms. So you guys don't need to worry about mechanistically how this happens or even kind of following along the electron count. Just wanted to show you guys that this is one way to make these sodium ethoxides. You can also do it with potassium, same thing works. And this is a very cheap way to make these alkoxide bases. Okay. Let's talk for a minute about the phenoxide ion. So here's phenol. Remember, that's a hydroxyl group attached to this aromatic ring. When we deprotonate phenol, I told you guys, I pointed out that it has a much lower pKa than most alcohols. So this acidity of phenol can be rationalized because what we get when we deprotonate, just like every other alcohol we deprotonate, we have a lone pair now on that oxygen. But in this case, when we have phenol, this lone pair isn't just stuck on this oxygen, right? Oxygen's a great place to put an extra lone pair and a negative formal charge because it's an electronegative element, so that's good. But in the case of phenoxide, we have an even better situation because our oxygen doesn't have to bear the weight of that negative charge all by itself. It can undergo resonance, and in fact it does. And so that negative charge is delocalized. It's not just on the oxygen, but it's also, if we push it down to make a new carbon-oxygen double bond, of course, then that carbon at the top of the ring would have 10 electrons, which we know is no good. So we have to break this pi bond and move those electrons to this carbon. So we can make a resonance structure where that oxygen is shared with this kind of carbon next to the carbon-oxygen double bond. And it turns out that can also be shared with the carbon at the bottom at kind of the 6 o'clock position. And we can keep doing this with our resonance structures and move that lone pair up to this sort of 10 o'clock carbon as well. And so the negative charge that on a regular alkyl alcohol, where there's not an aromatic ring involved, that negative charge would be only on the oxygen. There would be no place for it to go besides the oxygen. Here in the case of phenol, that negative charge is a little on the oxygen and it's a little bit on this carbon and this carbon and this carbon and kind of an every other carbon pattern based on how the electrons move in the resonance forms. And so the true structure, just like we learned in chapter 1, isn't any one of these things, but it's a hybrid between the 4 different structures that you're seeing here. So that negative charge will be partially on those 4 different atoms. And that explains the low pKa of the phenoxide ion. And so just as a reminder, right, this is the pKa range of regular alcohols is in the 16 to 18 range, but the pKa of phenol is 10. So if we do a direct comparison with the aromatic alcohol phenol and the non-aromatic counterpart where none of those double bonds exist, you can see we've got a Ka of 10 to the negative 10th for phenol 10 to the negative 18th for cyclohexanol. And so that means that cyclohexanol is 10 to the 8 times less acidic than phenol. Or another way of saying this is that phenol is 100 million times more acidic than cyclohexanol. All right, there's a question in the chat box that says, is that considered conjugation or just a delocalizing? All right, so let me go back to my resonance structures here. So when we're talking about conjugation, that's not a term that I've really introduced you guys to, I don't think, but you guys will learn more about it next semester. Conjugation actually just means pi bonds that are oriented in an every other position. So these pi bonds here are conjugated with each other. The term delocalizing is a better term for what's happening here because this negative charge will be, instead of being localized on the oxygen, it's going to be delocalized on that oxygen, this carbon, and this carbon. And all of these are resonance structures of each other. So they're resonance forms because we have left all of our nuclei in place. We've only moved electrons around, which means these are not actually different structures that are interconverting. These are 4 representations of a molecule, none of which is ideal to actually tell us what's going on in the molecule. So the true actual structure is something that looks like an average, probably a weighted average of these 4, where this one gets a little bit more weight because the negative charge is on an electronegative element. But because we're humans and our brains are limited in their capacity, this way of sort of depicting these 4 different forms which join together to make a hybrid, that's the better representation for the actual structure. These 4 forms are the best way for us as humans to kind of keep track of where everything is. I hope that answered your question. Okay. Okay, so like I said, the phenol pKa is much lower because of that resonance, and it's in fact 100 million times more acidic than the counterpart. It's like perfect structural counterpart that just doesn't have any of those double bonds in the aromatic ring. Okay, that's it for alcohol structure and properties. I am also going to just blatantly skip over alcohol nomenclature. I'm going to potentially save this for later. I will potentially cover this towards the end of the chapter, but I might not. It just kind of depends on how far we can get to with time, because these things down here are much more important than nomenclature. And nomenclature is also much easier to understand, especially because you guys have seen me talk about nomenclature for other things, and it's all kind of the same rules. So I do encourage you guys to review section 10-3 on your own. You will be responsible for nomenclature, whether or not I explicitly cover it in my slides here. Okay, let's move on and start actually digging into the synthesis of alcohols. And this is probably one of my favorite parts of this lecture, because you guys already know a whole bunch of ways to synthesize alcohols. So I want everyone to take 10 seconds, maybe 15, and just think on your own about a way, just one way that you know how to make an alcohol. And when you think about that, also think about where you're starting from. What do you need to do to, where do you need to start to get to that alcohol? So 10 seconds for everybody to think about that, or maybe 15. Okay, does everybody have a reaction in their mind? We're going to see if my reaction list covers everybody's reactions. All right, so first, hopefully you guys all thought of your wonderful chart from chapter 8. This is the 2 pages of the chart condensed into 1 page and with none of the information on the chart. But everything here with a star is a way to make an alcohol. So you guys already know these 6 reactions to make alcohols. You know 3 different ways to add water across a double bond. You know about the acidic hydration method, which doesn't work very well, but you know about it. You know about the oxymercuration demercuration method, which gives you a Markovnikov addition. You know about the hydroboration oxidation method, which gives you an anti-Markovnikov addition. You also know about halohydrin formation, where you can subject an alkene to bromine and water, and you can get halohydrin formation. You also know several different ways to dihydroxylate an alkene. Of course, this is our chapter 8 chart, so everything we're talking about is starting from an alkene right now. But you know these different ways to do dihydroxylation, either osmium tetroxide or mild potassium permanganate conditions to get a syn dihydroxylation, or a peracid with water to get a trans or an anti-dihydroxylation pattern. And you guys can review all of that from chapter 8. Other ways that you guys already know that aren't just from chapter 8, all the way back in chapter 6, you guys were making alcohols because you can do nucleophilic substitution of an alkyl halide using a hydroxide ion as the nucleophile, and that can give you an alcohol. Now for this one, you have to be a little bit careful because you can also get competing elimination, so you have to choose your substrates carefully, but it is a valid way to make alcohols. These next 3 bullets are the 3 categories of alkene reactions that I just talked about on the last slide: hydration, halohydrin, and dihydroxylation, and some of them with multiple methods. And then finally, you guys also learned in chapter 9 how to make alcohols using acetylides, right? So if you have a terminal alkyne and you treat it with sodium amide, then you can get the sodium acetylide. And that sodium acetylide can react with any electrophile, but one of the electrophile options here is to use a carbonyl. And when we use a carbonyl, like a ketone or an aldehyde, then that acetylide can react at the base of this carbonyl, which that carbon is electrophilic. We form a new carbon-carbon single bond, and we move these pi electrons up to be a lone pair on oxygen. And guess what? We just generated an alkoxide. So after we protonate that alkoxide, we have made an alcohol. So look at all of these different ways that you guys already know to make alcohols, and just think, you guys have been working on chapter 10 all along since like halfway through the semester. Okay, so I exploded this last one, the acetylides plus carbonyl compounds. I drew it out explicitly with all of its details because this is really all that chapter 10 is about also. There's, of course, going to be some more and some details and some subtleties, so we do have some stuff to learn. But what we're going to do in chapter 10 is learn about different types of nucleophiles, some specialized nucleophiles that we can use to do this same type of chemistry to get an alcohol where we have a different nucleophile here rather than just a triple bond. But it's going to very similarly and very closely follow this kind of a pattern where you have a nucleophile attacking a carbon-oxygen double bond, getting your alkoxide and protonating that alkoxide. And if we can get through that, we've got a lot of chapter 10 under our belts already. So let's go ahead and see what some of this stuff looks like. All right, so our new reactions that we're going to learn this chapter are going to fall into 2 broad categories. One is going to be organometallics, where we're going to use a specialized set of reagents that act like C-. The same way our acetylide was a carbanion, it was a C-. We have a whole set of reagents where we can create these reagents and they will act as if they are carbanions, even though they aren't actually carbanions running around loose in solution. And the second set are going to be a set of reactions where we can use H- to change a carbonyl to a hydroxyl group. And I'll show you both of these types of reactions in a bird's eye view on the next slide. And then after the bird's eye view, we'll drill down deeply into the organometallics today. And on Friday, we'll drill down deeply into the other topic. Okay, so here's the bird's eye view. This is a big picture overview of the main new reactions in chapter 10, which again is about alcohol synthesis. I want to point out for just a second, we are not doing any reactions of alcohols in this chapter, right? We are learning how to make alcohols so that we can react them later on. Reactions of alcohols are in chapter 11, and guess what? Chapter 11 is not part of this course. So what we're doing now, though, is laying the groundwork so that you know how to make alcohols so that in Chem 302, you can go and use those alcohols in some kind of an alcohol reaction. Okay, so one of the best ways to use alcohols is to use organometallic reagents and add those organometallic reagents into a carbonyl. So I'll talk about what I mean by that. The other way is to do what's called a hydride reduction of carbonyls. So the first way, and now let me actually take that away. Before I show you guys these, I want to take a moment and warn you guys, some of these compounds are going to look a little bit weird. We're out of the realm now of our comfort zone of carbon and just the atoms right around carbon. And we're having to reach out now and do some, like it says, it's organometallic chemistry. So we're working with some metals in the first and second column of the periodic table, but we're a little out of our comfort zone. We're a little bit getting into inorganic chemistry. But as organic chemists, we need to be able to use our inorganic chemistry to get the reagents that we need to get. So there are going to be some weird things that I'm showing you because we're not in our comfortable carbon only zone anymore. Sometimes you're just going to have to take my word for how things work and just run with it and just trust me on it. So here we go. Organometallic reagents. I'm showing you one example. This is the Grignard example. In future slides, I'll show you some lithium reagents. These are kind of an either or, and they're interchangeable. You can use either one. But in an organometallic reaction, what we've done is attach our carbon directly to a metal, and that carbon metal bond becomes highly polarized in a way that creates a lot of negative charge density buildup on the carbon because of how electropositive the metal is. And so what that carbon does is that it acts as if it's a C-. Whatever is attached to it, it doesn't really matter because the carbon is also attached to a metal, and that metal is so electropositive, it hates having electrons, so it's pushing electrons away from it and pushing that electron density onto the carbon. And so that carbon is going to be reactive as a C-. And that's how it's going to act. And it's going to be a strong nucleophile, just the same exact way we saw with the acetylide ions, which were also C-. They were a real C-. This one's not really a real C-, it just acts like it. But this carbanion equivalent is going to be nucleophilic, and so it'll use that electron density buildup to attack an electrophile, including carbonyl compounds. So when it does that attack, it forms a new carbon nucleophile bond, which is going to be a new carbon-carbon bond, pushes those pi electrons up to the oxygen, and we have our alkoxide product. Once we protonate this, we have made an alcohol. And so you can see how much this mirrors the acetylide reaction chemistry that we saw in chapter 9. For hydride reduction of carbonyls, it is exactly parallel to this. We're going to learn about some specialized reagents that essentially deliver for us a hydride ion. That is a hydrogen atom with 2 electrons, so it's carrying a lone pair. It's carrying a negative formal charge. And that is a lot of electron density to ask a hydrogen atom to carry around. And so it is going to be highly reactive. It is a strong nucleophile, and it will attack electrophilic centers, including carbonyls, which means we can use it to make alkoxides that after we protonate will become alcohols. So these are really going to be the 2 pathways that we're going to be talking about most this chapter. And again, I'm going to keep on saying this. This should kind of be a natural extension of things that you guys already know from chapter 9, where we can do this type of chemistry with acetylide ions. We can also do it now with organometallic reagents that act like R- or with hydrides. And so we'll talk today for the rest of class about this top one in kind of gory detail. So in order to do this, you can imagine these Grignard reagents are pretty reactive. So we have to make them ourselves, okay? So we are going to learn how to make Grignard reagents and lithium reagents first, and then we'll see some examples of using them to add into carbonyls. So here we go. We're going to focus the rest of our time now on these organometallics, and first by looking at the Grignard reagents. So for both of these sets, both the Grignard and the organolithium, these organometallic reagents, like I said, are reagents that can turn our normally kind of inert and benign carbon atoms into something that acts as if it's strongly negatively charged and can act as a strong nucleophile. And so all of these organometallic reagents will generate this, quote unquote C-, And that nucleophilic carbon can attack any electrophilic carbon. So any carbon that has a partial positive charge is a target for our nucleophilic carbon of our organometallic reagent, which means that we can react it with alkyl halides in an SN2 type fashion, or we can react it with carbonyls. And both cases, we're going to be making a new carbon-carbon double bond. So the carbonyl, just a reminder about why it's electrophilic, it's because we can draw a resonance structure where the pi electrons are on the oxygen already. And so that means that that carbon is a delta positive, a partially positive carbon, and electrophilic. And both of these methods, if you notice, we're going to have as our nucleophile a carbon atom that's acting as if it's negatively charged. And in both cases here, our electrophilic center is also a carbon atom. So these types of reactions are really good at forming carbon-carbon bonds. This is like a super duper awesome, useful, practical, functional way to make carbon-carbon bonds. And if you think about what organic molecules are, they're almost entirely made up of carbon-carbon bonds, right? So this turns out to be a super useful reagent set to know about. So let's know about it a little bit more. We're going to start with the Grignard reagents, and these are going to always have the generic molecular formula RMGX. And again, it's going to react as if that R group is a negatively charged R group with a carbon bearing that lone pair on, like in an anionic fashion. That's how it reacts, not how it actually exists. So here's the part where you guys are just going to have to trust me and not worry too much about the details here. We need to know how to make these Grignard reagents. So here's how you make the Grignard reagents. You take an alkyl halide, and you react it with magnesium solid, so magnesium 0. And just like we saw on an earlier slide that sodium is readily going to give up 1 electron to become sodium plus, magnesium is also going to be happy to give up 2 electrons to become magnesium 2 plus. And so when it does that, it's going to basically provide these 2 electrons to the alkyl halide, Rx. And what that's going to do is give us 2 additional electrons so that we can turn our 1 sigma bond into 2 sigma bonds. So the end result here is that magnesium is going to insert itself right into the middle of this Rx bond. And so we're going to get, instead of just 1 sigma bond in our business end of our molecule, we'll have 2 sigma bonds. And again, the electrons are coming 2 from that sigma bond and 2 from magnesium 0. And this organomagnesium halide is what's known as a Grignard reagent. It can have any R over here. It can have most halides over here. The iodides, bromines, chlorines are all very useful for organomagnesium halide reagents. Fluorides don't react very well, but the rest of the halogens work just fine. And the beauty of this is that we can do it with any alkyl halide. It doesn't matter what the alkyl halide is. If there's an Rx bond, you can put a magnesium in the middle of that Rx bond. Now, another thing to note, and I'll show you a different slide that'll drive this point home in a bit, but if you think about the polarity of our alkyl halide, that polarity is such that the electronegativity of that halide means that we have a delta positive on the carbon end of that bond and a delta negative on the halogen end of that bond. After we do this insertion and put magnesium in the middle, remember magnesium is so electropositive that it doesn't want the electrons near it. So it's going to push those electrons out and away from it. And that means that our R group, in addition to our X group, but our R group is going to have a delta negative now. And that means that we just switched our R group from being delta positive originally to delta negative in our organometallic reagent. It's pretty neat, huh? So you can see some examples of how to make these organometallic reagents. It is literally this easy. You take any alkyl halide that you want. You say, I'm going to put this in with some magnesium. And in the magnesium goes into the bond. Wherever the bromine was, it now becomes a magnesium bromide. So that magnesium is inserting right into this bond to make our 2 new bonds. And this phenyl magnesium bromide will act as if it has a carbanion right here at this corner carbon. So Grignard reactions are best done in ether. So you'll often see ether as part of the solvent, or it's the solvent, but you'll often see it as part of the equation. There's a lot of kind of advanced chemistry that go into the details of why, but it has to do with how the coordination happens with the ether lone pairs and the magnesium, and way beyond the scope of this course. But it is something that you often see with Grignard reagents, is that often they'll be described as being using magnesium and ether. So I just didn't want to leave that out. And here's another example, a secondary alkyl chloride. If we expose that to magnesium 0 in ether, then we get insertion into the carbon chloride bond, and we get this organometallic reagent, a Grignard reagent, where the carbon that I have circled in red here is going to act as a carbanion. All right, so I told you I'd show you this again, but here's an electrostatic potential map of iodomethane. And you can see, remember, red is for negatively charged, blue is for positively charged. You can see our molecular dipole being played out in this molecule, and exactly why the carbon here in iodomethane is electrophilic, because the electronegativity of that iodine is pulling all of the electron density towards it from this bond. What happens when we make a Grignard reagent? Well, we stick that magnesium right in the center. That magnesium has inserted into this carbon halogen bond now, and that magnesium is so electropositive that it flips around the dipole of the bond coming off of that carbon. And so now we have a negative charge buildup on the carbon. The same exact carbon that used to be delta positive now has a negative charge buildup and is delta negative because of being now bonded to a strongly electropositive thing and not a strongly electronegative thing. I don't know if you guys remember, but all the way back in chapter 1, possibly even on day 1, I showed the second row of the periodic table, and I noted how carbon is right in the middle of that row of the periodic table. And that is what makes carbon so cool, is because it kind of can play either side of the field here. And so that's exactly what's happening here. We can use carbon as an electrophile if we have our molecule set up right. But now that we know how to make Grignard reagents, we can also use that same exact carbon atom and turn it into a nucleophile. And so that gives us a lot of power as synthetic chemists. Okay, there's a question in the chat box that says, is the carbon more electronegative than the I in that example? That's a good question. No, I don't think so. So first of all, you got to be really careful. Carbon, the term electronegative is a reference to an atom, not in a molecule, right? And so iodine is always going to be more electronegative than carbon. But what the question you're really trying to ask here is about a delta negative or a partial negative charge, or the negative charge buildup. And so what I would say is that both the iodine and the carbon here are going to have a delta negative charge. Probably the iodine has a bigger delta negative charge, but it's also more capable of stabilizing that negative charge because of its electronegativity, right? Whereas the carbon atom is going to be carrying a delta negative charge in this Grignard reagent, but it is not an electronegative element, and so it is unstable. So the reactive side of the molecule will be the carbon side of the molecule. Good question. Okay, now that we know how to turn our carbon atom from electrophilic into nucleophilic with a Grignard reagent, let's talk about organolithium reagents. So I've been talking about, you can use either this or that, but I haven't actually introduced you guys to organolithium reagents yet. The first thing to know is that it's just like a Grignard. It works the same way. You can pick whichever one you want in a situation and it'll be fine. It's the same end result. There's not really a whole lot of difference between one and the other. Biggest difference is that Grignard reagents really do better in ether, but for organolithium, you can use a lot of other solvents as long as your solvent does not have an acidic proton. So we cannot use any water or alcohol-based solvents here because our Grignard reagent or our organolithium reagent in this case would just deprotonate it. And I'll talk more about that later. Okay, so here's what this looks like with making our organolithium reagents. We can do we're going to up an electron so that it can achieve an inert gas electronic configuration of lithium plus. Uh-oh, I'm getting an internet connection warning. Can you guys still hear me and see me? Okay. All right, so our lithium is ready to go to give up an electron. And we're gonna now need 2 moles of lithium for every mole of alkyl halide because we need to use 2 electrons to generate our X minus and our R minus, right? So if you imagine what we wanna get to is we have an Rx and we wanna get to R minus and X minus. So we're gonna need 4 electrons total to do that. 2 of them are gonna be in this bond. The other 2 are coming from lithium. So it's the same exact type of chemistry, but in this case, because lithium is in column 1 of the periodic table, we just have an organolithium. We don't have to have that halide on the other side. The halide actually pairs up with another molecule of a lithium ion and becomes a lithium salt. Other than that, everything here is exactly the same. So let's see that in action. This is also just a reminder. It's the same thing that we just did before with the organometallic, the Grignard reagent, the organomagnesium reagent. Organolithium reagents work the same way, where in our original alkyl halide, that carbon is delta positive and electrophilic. But when we change out our carbon halogen bond for a carbon metal bond, the polarity of that bond is reversed. And so now our carbon is delta negative and nucleophilic. So same kind of concept as what we just saw with the organomagnesium reagents or Grignard reagents. Okay, so here is an example of a primary halide, where if we incubate it with lithium metal in hexane, we can get butyllithium. Butyllithium is a hugely useful organic reagent. You can use this for all sorts of different things in the lab. You can do it doesn't have to be a primary alkyl halide. You can do it with any alkyl halide. So here is a vinyl chloride, where our carbon chloride bond, our chloride is attached directly to a carbon that's sp2 hybridized from being part of an alkene. And here is an aryl halide or an aromatic halide that after treatment with lithium becomes a phenyllithium, where the carbon directly attached to the lithium right here acts as an anion. Okay, now that we know how to make these organometallics, I'm going to spend just a couple of minutes reminding you guys of what you already know about how to use them. These are going to act as a C minus, and so they are going to attack at the base of a carbonyl to make our new carbon single bond, push these pi electrons out to the oxygen, and then we'll be at an alkoxide that after we protonate can give us our alcohol. So just a reminder, this is going to mirror the acetylide reactivity directly. So a direct mirror of chapter 9 reactivity. And the other thing I want to remind you about is that this has to go in 2 steps. The first step, our nucleophile attacking our carbonyl to get our alkoxide. And in a separate step, a completely separate step, step 2, a different step, we can quench our alkoxide by providing a proton source. This can be water, it can be H3O+, it can even just be a generic H+. But this quench is important to get to our alcohol because here we don't have an alcohol yet. So we got to get to an alcohol. And this quench has to happen in a separate step. It has to happen in a separate step because if we tried to have the quenching reagents around here, it would not produce this alkoxide to quench. It would quench our organometallic reagent, right? Think about what this is. This is a carbanion, which you know has a really high pKa. And so that means that not only is it a really awesome nucleophile, it's a super awesome base. And so if you put this R minus or quote unquote R minus in with water, you will not get this addition to a carbonyl. You will get a new RH bond. That's what you will get. So I'm going to show you the last couple of slides super quickly here to point out that now we need to be thinking about synthesis-oriented thoughts. And so I'm going to show you 3 different ways to apply this. The first way is to get a primary alcohol. So if we have a synthetic target that has a primary alcohol, this is one way that we could generate that. We can take an organometallic reagent, it can be a Grignard or an organolithium, and we can react it with this carbonyl that is substituted by two CH bonds. This is a special carbonyl called formaldehyde, and it's a way to generate a primary alcohol, because if you think about mechanistically what's happening here, you're forming a new carbon-carbon bond with your nucleophile that's here. These two CH bonds are essentially like spectator bonds, but that means that in the end, after you protonate in a separate step, what you will have gotten is a new hydroxyl bond on a carbon that is a primary carbon. And so therefore you have a primary alcohol. So I'll pick up here next time, but I want you guys to think, knowing this and seeing this, how would you make a secondary alcohol, right? Think about what you would need to make a secondary alcohol and think backwards about how in that secondary alcohol where two of these bonds are going to be carbons, one of these carbon bonds is going to have come from a new carbon-carbon bond. So think backwards about what your carbonyl would look like for a secondary alcohol. And then when you're done thinking backwards about that, think backwards about what your carbonyl would look like if you wanted to make a tertiary alcohol. And we'll pick up here on Friday. Thank you guys for your attention. And don't forget, I have office hours today at 3, and I can stick around for a couple of questions.